This is our last day. So, Pre-Calc Chapter 4, Min, Max Problems. This will be your last notes for the chapter. These are taking our application problems from day 14 and 15, and now we're just adding one last part, which is max and min. So we're going to do everything we did before, and then the very last step is to find that max or min. Okay, find that vertex point from the equation that we create. So, a couple tips. We're going to want to find one equation and one function. We're going to write the function in terms of one variable, and then find the max or the min. We actually don't need to solve the function. Okay, so we're going to be really careful about these directions. If it just wants the max, then we'll just give it the max. No need to actually solve fully. So we'll do a bunch of examples today. I know this will be a little bit long, but this will be the last time you'll watch a video for chapter 4, so let's power through. Okay, vertex of a quadratic-like function. Example, find the max or min of the function here. So we've talked about max and min before. You know it's going to be the opposite of the term in the parentheses, so positive 2, and it's going to be the same as the term outside. Okay, that is the vertex for just the equation inside. Well, if we find the x value of the vertex of the baby function, we can apply it to the big function. Okay, remember that? This is like our x naught, we called it. That's going to be the same x value for vertex of the highlighted as well as the square root of the highlighted. However, the y value will change. I'm going to plug in my x naught of 2, that same x value. When I plug it in, 2 minus 2 squared plus 3, I get that if I plug in 2, my value will be root 3. So it wants me to find the min or max of the function. Well, the min of this function is going to be the point 2, root 3. Okay, and you can see that if you actually graph it, that will be the minimum. We first found it from the easy function and then applied it to the big function. Okay, so that is a lot of the stuff we're going to be doing today. Example 2, the sum of two numbers is 1. What is the largest possible value for their product? Here's a little graphic that we can use if you want. We've done something similar to this before. The sum of two numbers is 1. You don't want to write x plus y equals 1. Right? That's too many variables. So instead, I can do x plus 1 minus x will equal 1. This is a true statement for any x. That's the sum. I want the product though. So product of those two terms, because I can just write an equal sign, is going to be x times 1 minus x. So the product is really x minus x squared. This is normally where we end, right? We said this is the product, we've done this, and we're good to go. However, this problem adds one more element. It says the largest possible. So we want to find that vertex. We want to find that largest possible value. So today we're going a step further. We need to find the vertex. There's two ways to find the vertex. You can decide to complete the square. That will give you your vertex. We've been pretty good with that. Or you can use the vertex formula, which I think it's helpful if I rewrite it like so, right, in the correct order. But vertex form, the x value equals negative b over 2a. That should be familiar to you. You can either do this way or complete the square. When I do it this way, I get my b value is 1 over 2 times negative 1. So my x value of my vertex is 1/2. I need to now find my y value, so I'm going to take that, plug it back in. So my p or y value in this case is going to be negative 1/2 squared plus 1/2. So I get 1/4. So the problem asked, what is the largest possible value of their product? We found the x value and the product. So I'm going to write my final answer. The max product is that y value is 1/4. Okay. So blue is what we've done before. Purple is the new addition with max min. Just find that vertex. Example 3, you have 100 feet of fencing for your pig farm. What rectangular dimensions produce the largest possible area? What is the area? Okay, again, here's a picture to look at. We're trying to find the largest possible area. So I'm actually shooting to find this point right there. Okay, just a little bit of what we're doing. So let's start out with what we've done before. I know I have a little pig farm. I'm going to call this side X. This one will be X. It is rectangular because it tells me Y. And I know you have 100 feet possible. So my perimeter is 100, which means 2x plus 2y equals 100. That's just what I'm getting from the first sentence of our problem. Our goal is to find area. So right, this is what we're trying to find, area, which is going to be base times height. This is our goal. But I can only have it in terms of one variable. We know that. So let's solve for a variable and plug into our area formula. I'm going to get x by itself. I guess I can get y by itself. So 2y is going to equal negative 2x plus 100. Y will be negative x plus 50. Okay, this is from before. I'm just getting area into one variable now. I'm going to distribute. Negative x squared plus 50x. Okay? Normally this is where we stop. We find the area formula. But now it wants us to find the largest possible area, which means that vertex. So one step further, you can again complete the square or use vertex form. So I'm going to use vertex, which just means the x value will be negative b over 2a. Negative 50 over 2 times negative 1. So my x value is negative here, is a positive 25. Let me find my corresponding y value. If I plug back in, or I guess a value, because we don't care about the y value here, it just says find the area. So if I plug this back in here, I get the area to be negative 25 squared plus 50 times 25. So my max area is going to equal 625 feet squared. Again, blue is what we've done before. We're now going a step further, finding that vertex point. And you actually can kind of tell that it would be 625. Yeah, that actually looks right on our picture. Okay, doing great. Suppose that a baseball is tossed straight up and its height as a function of time given by this function. H of t equals negative 16t squared plus 64t plus 6. where h of t is measured in feet, t is in seconds, and t equals 0 corresponds to the instant that the ball is released. What is the maximum height? So actually all the work is done for us, right? This is the part that we would have got to in our last set of notes. It wants us now just to find the maximum height of the ball. So we're trying to find that vertex again. You could complete the square, or you could do x equals negative b over 2a. I'm going to show completing the square just as a little difference because you know both will work. So when I complete the square, quick reminder, we have to factor out that 16 because we need a 1 as the coefficient to become minus 4t, and then I move over that plus 6 a little bit. I'm going to do my complete the square now, which means in here I do b divided by 2 squared. So negative 4 divided by 2 is negative 2 squared is 4. So I add 4 here. And remember, you can't just add a number to one side and think that it's even. You have to remember that instead of just adding 4, you really have 4 with a factor of negative 16. So I really subtracted 64. Undo a subtraction of 64 means add 64. All these fun rules coming back at us. You're like, oh, maybe I should have done the other way. It doesn't matter. We know we did it right if we can get this factored to a squared term. And we can. It's going to be t minus 2. So my vertex, looking at it, is going to be positive 2, positive 70. Let's answer what the problem wants. It wants the height, that y value. So the only answer we need to give it is the 70. So max height equals the 70 feet. So please be very specific. If I want the height, give me the height. If I wanted the time that it's the maximum, you would say 2. Okay, 2 seconds gives us that maximum height. Dimensions that maximize an area. Suppose you have 600 meters of fencing with which to build 2 adjacent rectangular corrals. Notice the picture here, it's very, very helpful. The 2 corrals are to share a common fence. Find the dimensions x and y so that the total enclosed area is as large as possible. Okay, let's go to what we did before, is we actually find that area. So my goal is to get area. As always, we have to have it in terms of one variable. So let's look at what we're given and try to replace either x and y to get one variable for my area. Let's see, this whole length is going to be y. I know we have 600 meters of fencing, so my perimeter in a way is 600. So 600 is going to equal, I have 2 y's, right, 2 sides, but I also have 3 x's because I need to make this part of the fence. So I actually have 3 x's, that we'll have to include in that 60 meters. Let's solve for a variable. Let's say let's solve for y. That's always nice. So 600 minus 3x equals 2y. I'm going to kind of rearrange a little bit for us. So y is going to equal 300 minus 3/2 x. Ugh, fractions, but it's okay. We're taking that, plugging it in. This is everything we did before. Now we get a nice function of negative 3/2 x squared plus 300x. this is the area function, and we would have been done if it didn't say as large as possible. That tells us maximum. We're going to try to find that max value. Okay, so going just a little bit further. We now want the maximum, so I'm going to do vertex formula, x equals, negative b over 2a. So we'll get negative 300 over 2 times negative 3/2. So my x value is going to be positive 100. Reading the problem, it wants me to actually just find the dimensions. Well, that's actually really nice. Okay, I just need x and I need y. I don't even need to plug in for the area. That's great. So I'm going to go back here, plug in my value to solve for y. That's what the problem wants me to do. So 300 minus 3/2 times my x value. And then I get my y value to be 150. Okay. So x in the end is 100 meters. Y is 150 meters. And that's what it wanted. We found that area function in terms of one variable. Then we found the max, which is x and y. Example 6, a demand function relates price and the number of units sold. Revenue is defined as price times number of units sold. If the price function is defined as so, find the number of units sold that maximizes revenue, and what is that maximum revenue? This should be familiar. This was on day 14. Now we're just taking it a step further. Okay? We're trying to find this max point now, not just the function. We want a little bit more. So quick recap from day 14. What we did is we took revenue, which is price times number of units. We took our value right here, there we go, plugged it in for price, negative 0.50x plus 60, and x is the amount of units sold, so we just times it by x. So my revenue function that we found from before is as so. This is review. Now we just want to find the max. Okay, so we take this as if it was a quadratic. Look at the picture. That red is the quadratic that we just graphed. Now we're going to find the vertex for it. Okay, so vertex, negative b over 2a. You're probably getting tired of that by now, but it's okay. So my x value of my vertex is 60. It wants the max revenue, and what is that max revenue? So I just have to take this x, plug it in. This x value will give me my maximum. So the revenue, negative 0.5, this is 60 squared now, plus 60 times 60, because that's what x is. So my max revenue is going to equal, it's 1,000, I don't know what that symbol is, but $1,800. What is going on? Okay. And if you look at it, that kind of similar to where the graph hits that maximum point. I would say that's like 1,800. So you know we did it right. Example 7. We now have two functions. Find the minimum value of a minus b. Well, first thing is we need to find what is a minus b, and then we'll find that minimum value. So we'll start with what we've done before. A minus b. Well, a is 3x squared plus 4x minus 5. And I'm subtracting. Notice my parentheses here. I'm going to distribute properly because I don't want to make any silly mistakes right at the beginning. Minus x squared plus 4x plus 1. I'm going to combine some like terms. I'm going to get 2x squared plus 8x minus 4. Now, it doesn't have a name for it, but I'm just going to call it y. Because now, this is something that I can find the max of. Treat this as a regular quadratic function. I'm going to find the minimum because it's going to open up. So this is what I normally would do, but now that it has the word right here, minimum, I need to go a little bit further. Let's find that vertex. So, completing the square is always an option as well, but let's make our lives a little easier. It would be negative 8 over 2 times 2, so that x value will become negative 2, which means the corresponding y value, when I plug it back in, make sure you square, I'm getting negative 12. So we found the quadratic, we found the minimum, and now it wants the minimum value. So we need to realize that's the y value. So minimum value will equal negative 12. Okay, one last one. You guys can do it. Power through. Last example for chapter 4. We're going to talk about a liquid storage container on a truck. What you guys have always thought about and dreamed about is in the shape of a cylinder with hemispheres on each end. The total length is 140 feet. I'm actually going to just draw that in so I can visualize what's happening. And the cylinders and hemisphere have the same radius. Determine the volume as a function of the radius x. Hey, this one doesn't even care about max and min. That's great. So I don't have to worry about finding a vertex at all. I can just solve it like a normal day 14, day 15 problem. So yay for us. We want the volume. So quick reminder, what is the volume formula? You will be given these, or you can look at that geometry sheet that I gave you on day 14. But the volume, you're going to have to add in together the cylinder, so that middle part, plus if you have two hemispheres, do we all see that that's going to be really one sphere? 1/2 and 1/2, put it together, you get one nice solid sphere. So I'm really finding volume of cylinder is pi r squared h. Volume of a sphere is 4/3 pi r cubed. Again, you don't need those memorized. Make sure you just have that sheet accessible. Okay, I want volume as a function of x. So this is what I want, but I can only have x. I have an h in there. Radius is x, so really all those r's will be x's. Somehow I need to get rid of h. Let's figure out what we got. I'm going to draw a little bit more here. They said our radius is the same. So from here to here and here to here, it's going to be the same distance. It doesn't look like it, but it says they have the same radius. Okay, so this radius, let's call it x. This distance is x. So I want to find a new way to represent height of my cylinder. I want a new way to represent this squiggly line instead of h. Well, kind of look at it. If the whole thing's 140, this was h, so x plus h plus x equals 140. So 2x plus h equals 140. H can now actually be written as 140 minus 2x. Right here, another way is 140 minus 2x. Take that bad boy and plug her on in. And then I only have to deal with my x's, my radius. So I'm actually just going to make my life a little bit easier. I'm going to call these x's just because that's what it said in the problem. Now I can write volume in terms of just x. Volume equals pi x squared times 140 minus 2x plus 4/3 pi x cubed. Looking at it, I could distribute, but I did what it asked. I have a volume in terms of x, and this is where I can stop. If it asked for max or min, that's when we would keep going, but this problem didn't. So if you learned anything from today, it's to read carefully, it's to take everything we did before, and now just add in the max or the min. We'll talk about any questions you guys have in class. Good luck, you made it through. I'll see you soon.